they still didn't issue a veto. They didn't be inactive. I emailed them, but I forgot to put the email. So I didn't get back.
Will you still be able to?
I think Sunday was last day.
Oh man,
Okay.
because otherwise I was going to do class to cancel.
Yeah.
Cut the flu. Man.
So now it looks like all of those updates for my tab.
Yeah. And it crashed.
Updated on when I got to the other
Right.
page, and the version of the notepad, OneNote I was using,
Yeah.
no longer was like it was no longer supported to read over. So I was sitting there going like, well, you gotta figure out what to do now. Middle of right when class started.
I have a question. So, for the home, do you want us to also submit the dotting file?
No, it's okay.
Okay.
Because you're just using it to solve the matrices, and so I trust that I mean they're all just going to look the same. So,
Okay.
yeah. Mhm. All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today?
Pretty good.
Good to hear. So I had a little bit of a rough weekend. Not well, I got sick, but that's not because of the weekend was rough. So Friday was my mom's birthday, and I committed the cardinal sin that no child should ever do, and I forgot my mom's birthday. The funny thing is my dad actually gave me an out. So he calls me, which happens a lot nowadays because he's they're always like, oh, I want to talk to my grandson. So my dad calls me and he's like, does Isaac want to say a happy birthday to grandma? And I should have just played along. I should have just been like, oh yeah, happy birthday, grandma. But then I gave the worst reaction. I was like, oh yeah, it's mom's birthday today. And then so my mom is very mad at me right now. So the other thing I forgot, yesterday was my wife and I's anniversary, actually. But that one's okay because my wife also forgot. So actually, I was the first one to remember. So I came home with flowers, and she's like, "Oh yeah, it's our anniversary." So yeah, when you have a newborn kid and you're not getting sleep, then everything's crazy. So but anyway, so I'm alive for now. I'm scared to talk to my mom, but we're all good. Okay, so today agenda for today is just truss equations. And so, we basically got right up to the end of the derivation of the 2D element stiffness matrix. So we'll finish that up today. And then the rest of today is basically just examples. And so, what you're going to see is that for 2D problems, nothing really changes. Our whole finite element process is still exactly the same. The only thing that's going to change is that the problems get a lot more tedious and a lot more annoying. And so I think a few of you have already kind of seen this. And so I know a few of you have already kind of started on the 2D problems in the homework. So you know exactly what I'm talking about, but there's no painless way to go about this. We just have to kind of drive right into it. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and pick up where we left off. Okay. So where we left off last time was we were looking at basically element stiffness matrices for trusses. In 2D. Okay. All right, so let's just summarize some of the key points in terms of why 2D problems are challenging compared to 1D problems. Okay. Okay, so first of all, let's remind ourselves that truss elements truss elements are basically structures that can only support tension and compression. Okay. So we have our truss element here, right? Usually when you make a truss element, it's going to be very slender, so it's going to be much longer than it is wide. Okay. And it can only support deformations and forces down its member. Okay. And so another way to describe this is that it can only support axial deformations. Axial being, the direction down the length of our cylinder member. Okay. But a lot of times it's easier just for me to say tension and compression. Okay. Now, under this assumption, we very easily kind of derive the element stiffness matrix for a truss in 1D. Okay. So we basically say the element stiffness matrix is AE over L, 1 minus 1 minus 1, 1, D1, D2. Okay. And that was perfectly fine for our 1D problems because one thing that occurs in 1D, that was kind of implicit that we didn't really explicitly say, is that all of the axes or all of the directions for deformation, no matter how many elements that you have, they all line up exactly with each other because the problem is exactly in 1D. Okay. Right, so we can basically approach 1D problems very, very simply. So we just, take our element stiffness matrices as they are. Of course, they're all going to have different values because they're going to have different values of, geometry, different lengths, areas, different Young's moduli, and just, plug them right into our global linear system. Okay. In 2D, this is no longer the case, right? In 2D, right? In 2D, our truss elements can have different orientations. And so, you might have a structure that looks like this, right? Right, just to put it very simply. So if we work under the same assumption that our truss bars can only support tension and compression, right? So element A on the left here can go this way. Element B on the right can go this way, right? Right. The tension and compression of one element is not going to be aligned with tension and compression in the other, right? Just because they're facing different directions, okay? And so when we have this occurring, we can't just directly compare. We can't directly add together element stiffness matrices for these elements, at least as we had it before. Okay. So our solution to this, right? Our solution to this is to basically work under a unified coordinate system that all elements have to adhere to, okay? We call this the stationary coordinate system. Now, the problem with the stationary coordinate system is that, most of the time, this stationary coordinate system is not going to be aligned with our elements, okay? And so that's going to change the appearance or change the form of our element stiffness matrix, okay? Now, the way that we did this, or the way that we derived this, is we did this through coordinate transformations, okay? Now, I'm not going to go through all of the details of that proof last time. I think we spent quite a bit of time with that. But kind of the upshot of that entire thing was that we can basically pre-multiply and post-multiply a transformation matrix to our element stiffness matrix. Excuse me. Okay, and then we stop basically right there, right when I was about to kind of write the result. Okay. Okay, so let's write that result now. Okay. Okay, so the element stiffness matrix for truss elements in 2D, okay, is given by the following. Okay. Okay. Right. So first we have AE over L, right? That's going to be present for every truss element that we have. Okay. And this will be multiplied by, remember, since we're in 2 dimensions now, we have to account for X and Y deformation for both of the nodes. And so our element stiffness matrix goes from a 2 by 2 to a 4 by 4. Okay. Okay. And so I'm going to write everything first, and then we'll kind of go back and look at it again after that, because if I'm not paying attention, I might miss a negative. So okay, so we have c squared, that's cosine squared, and cosine times sine minus cosine squared minus cosine sine. Okay. We have sine squared minus cosine sine minus sine squared. Okay. And then third row, we have cosine squared, cosine sine, and then bottom right, we have sine squared. Okay. And the reason I'm only writing in half this matrix is that this matrix is symmetric. And so what that means basically is that, everything, basically, you can write out, all the missing columns, you can write the same as the rows, okay? So for instance, this first column here is going to be exactly the same as that first row. So this entry here is going to be CS, right? Then we have minus cosine squared, minus C squared, then minus cosine sine, okay? And then in the bottom, the second column here, the entries that are missing are minus cosine sine, and then minus sine squared. And then on the bottom term, the one that's missing is just the reflection of cosine sine. So cosine sine, okay? Okay, and this is D1x, D1y, D2x, D2y. Okay. All right, so what are all these C's and S's? So remember C here, this is cosine of the angle. Okay. And then S is sine of the angle. Okay. And what is that angle? That angle is the angle that's formed between the orientation of your element and the positive x-axis in the stationary coordinate system. All right. All right, so you can see why I kind of, didn't want to squeeze this in the last, 12 seconds of class last time. It takes a while to kind of write all these terms. Okay. Any questions on this or just, anything from the recap that we went over last time? Okay. All right, so before we jump into some examples, let's talk about that angle a little bit first, because that angle, I think, is probably the most confusing part of this, this whole thing, okay? Okay, so that angle is the angle that forms between the truss element and the positive x-axis, right? But that's assuming that you rotate only from the counterclockwise direction. Okay, so for example, right? So let's say we have a truss bar that looks like this, right? So it's oriented up like that. We have our positive x-axis, the stationary one. Traditionally we have it as just horizontal, okay? And so the angle that this element makes with that positive x-axis there is theta, right? We can give it a value. So, this looks kind of looks like 30 degrees, okay? So that's our angle, right? So pretty straightforward, okay? Okay, let's look at another element. Okay. So let's say that, it looks kind of the same, but instead, let's say that node 1 is up here and node 2 is down there, okay? Now, this part's really important. So when you're determining the angles for an element and you're trying to determine where to draw the positive x-axis, you should always draw it at the, you should always have your origin at the lower numbered node, okay? And so I'll make this red. Okay. Okay. So why do we do this? There's nothing that special about the lower numbered node. It's not a strict requirement for running the direct stiffness method. The only reason I have that is is just to stay consistent. Okay, you can get the exact same solution if you put the x-axis on the higher number node. You just have to be kind of consistent with it. Okay, so to kind of just make things kind of simple for the class, I would say just put the origin at the lower number node and then measure your rotation from there. Okay, so for this case, the lower number node is node 1. Okay, so we're going to draw our x-axis that way. Okay, so what is the angle that we're actually going to plug in here? Remember, we measure the angle rotating counterclockwise from the positive x-axis. Okay, so in this case, the angle that we plug in is actually going to be this one right here. Okay, it's always tempting to pick the acute angle. It's always tempting to pick the smaller one, but you have to be kind of consistent when you're applying these angles for these element stiffness matrices. Otherwise, you're going to get the wrong result. Okay. So in this situation, you can see we rotate over 180 degrees, and so I'm just kind of eyeballing this. This maybe looks like 225 degrees of rotation. Okay. All right. So why is that important? And so this might seem extremely pedantic, but it actually does make a difference in your solution, right? Because the values for sine and cosine are going to change depending on the value of the angle that you put in, right? Because cosine of 45, right, is not the same as cosine of 135, right? So even though in both cases, we have kind of a quarter turn, right? In one sense, cosine of 45 gives you a positive one, and cosine of 135 gives you a minus one. Okay. So it might seem kind of silly at first, to measure these kind of big sweeping angles, but it actually does make a difference when you actually plug these in. So you want to make sure that you get those angles correct. So that's the number one kind of source of errors and source of confusion for these types of problems. Okay. All right. Any questions on that before we jump into an example? Okay. All right. So let's go ahead and do an example. Okay. All right. So this is our first 2D problem. Right. This is about as simple as it can get. Okay. So let's look at it. Let's look at an assembly of truss elements and one spring element. Okay. All right, so let's say that we have a pin support up here. We have one element that comes down here, so that's going to be a truss. We have another one that's forming a 90-degree angle to that. Just like that, okay? And then let's say that we have a spring that's attached to this as well, okay? By the way, that element stiffness matrix that we derived for the truss, you can easily apply it to the spring as well, okay? Because what did we see from before? Trusses and springs are actually extremely similar. So they both can only support tension and compression. The only thing that's different between the two is just the coefficient out in front. And so for truss elements, you have AE divided by L. For spring elements, you have the spring constant K. Okay. Okay, so let's go ahead and start labeling the elements and nodes. So let's say that this element here is element A. We'll call the spring element element B. And we'll call the other truss element C. All right, let's label the node. So let's say that the node down here is node 1. The one attached to element A is node 2. The one attached to the spring is node 3. And the one attached to this one is node 4. Okay. All right, so for this problem, let's also put some numbers in just so that we can get an answer. Okay, so elements A and C are identical truss elements. And so their properties are the following. So let's say the Young's modulus is 30 times 10 to the 6 psi. We'll say that they have a length of 10 feet and a cross-sectional area of 2 inch square. Okay. Okay, and then element B. Element B is obviously a spring. And so, we'll say element B has a spring constant of 250,000 pounds per inch. Okay. All right, and so what we want to do in this case, and so we have, I always forget this, we need our loading, okay? So this structure is not going to do anything until we actually apply a load. So let's say that at node 1, we're going to apply a vertical force of 10,000 pounds. Okay. Oh, we also need our angles here too, okay? Okay, so let's say that the angle between elements B and C is 45 degrees. And then the angle between element B and A is also 45 degrees. Okay. Sorry, I should have mentioned that. I know we're kind of going back and forth on the right and left. Okay. Okay. And so with all this information here, let's use that and solve for the deflection of node number 1. All right. All right, so this is our first 2D problem. So, we're going to have to, do with that. But, like I said before, all of our finite element problems follow the exact same process. The only thing that really changes is just the details of the element stiffness matrix, okay? Okay, so let's go ahead and apply that same process. And so let's go ahead and first compute the element stiffness matrices for all 3 elements. Okay. All right, so basically, we're going to go up here and we're just going to plug into this. And so there is no pretty or elegant way to do this. As you kind of do these more and more, you start to kind of get some shortcuts in your head. And so, right away, I know what it should look like for 0 degrees, 45, 90. But when you're just starting out, there's no pretty way. You just got to plug everything in. Okay. Okay. So the way I like to do these is that, I go element by element. And first I take note of what the angle should be when we plug in to our element stiffness matrix. Okay. So let's start with element A. Okay. So first thing, let's determine what the angle is or what the orientation for element A is going to be. Okay. Remember that angle there is the counterclockwise rotation angle to get the element into the orientation that it's in right now. Okay. All right. So if we start, right, if we start from the lower numbered node, which in this case is node 1, okay, we start from the positive x-axis and then we rotate counterclockwise to get the element into the position that it's in. We can see that we've rotated 45 plus 45, which equals 90 degrees. Okay. So the angle for element A in this case is 90 degrees. Okay. So 90 degrees is very nice because that means we're going to have sine of 90 or cosine of 90 degrees is 0, right? So cosine of 90 degrees is 0. Sine of 90 degrees is equal to 1. Okay. Okay, so let's go ahead and plug that into our element stiffness matrix. And so we have AE over L. Okay. We'll plug in for that in a second. Okay. But first thing, let's go ahead and plug into everything in the in the matrix here. Okay. Okay, so let me go ahead and write. Let me go ahead and write out the all the terms here, just so we can just so we're not scrolling up and down. Let me go back in my notes for that. Give me just a second. Okay. So for a 2D truss, our element stiffness matrix is AE over L times cosine squared, cosine sine, minus cosine squared, minus cosine sine. Second row is sine squared, minus cosine sine, minus sine squared, cosine squared, cosine sine, sine squared. And of course, this is all symmetric. Okay. So one trick to kind of make things a bit easier is just to compute things in the upper right quadrant of the matrix and then just reflect it over to the bottom left. Okay. Okay, so let's go ahead and start plugging in. Okay, so for an angle of 90 degrees, basically any term with cosine we know is going to be zero because cosine squared, cosine 0 times 0 is 0. Cosine sine is 0 times 1, which is 0. Okay, so that entire first row is going to be zeros. Okay, because there's a cosine in every single term in that in that row. Okay. And then before we move on to the second row, let's take advantage of the symmetry in our element stiffness matrix. Okay, so let's take the first row. Let's take the entries of the first row and write them into the first column. Okay, so basically, you can think of it like this. So, think of the first row kind of just kind of rotating downwards into the entries in the first column. Right. So this one's not that exciting because they're all zeros, but this is 0, 0, 0. Okay. Okay, good. All right, so then let's write the entries in the next row. So the next row is starts with sine squared on the diagonal. So sine squared in this case is going to be 1. Okay. Next, we have minus cosine sine. Since cosine is 0, we're just going to get 0 for that. And then we have minus sine squared, which is minus 1. All right, so just like we did with the first row, let's take the entries in this row and just rotate it down. Let's reflect it across the diagonal. Okay. All right, so we're going to get 0 and then minus 1. Right, we're just kind of building up our element stiffness matrix row by row. Okay. I know this is very tedious, I'm aware, but at least this symmetry trick will save you a little bit of work. Okay. All right, next row we have cosine squared and then cosine sine. Both of those have cosine, so that's just going to be zeros. And I'm going to do my trick one more time. So we're going to rotate that 0 down into the last row. Okay. And that last entry there is just a sine squared in the bottom right. Sine squared is just 1. Okay. Okay. Good. All right, and then we're going to multiply this by our vector of degrees of freedom, which depends on the nodes that this element is attached to. Okay, so for element A is connected to nodes 1 and 2. So that means our solution vector here is going to be d1x, d1y, d2x, d2y. Okay. Right, and then AE over L, we can just go ahead and plug in for those as well. So we know A is 30 times 10 to the 6 psi. L is 10 feet. You have to be careful with this because remember, when you're doing calculations, they all have to be within the same units. And so if you look at all of our other units here, they're all in inches, not feet. And so we have to convert this 10 feet to 120 inches. Okay. And then our area here is 2-inch square. And so we plug all those in. We get AE over L is 5 times 10 to the 5th pound per inch. All right, any questions on this this problem up to this point? Okay, good. All right, so let's go ahead and repeat the same thing for the other two elements. Let's do element B next. That one's definitely the more challenging one. Okay. Okay, so element B, that's our spring. So let's go back up here. First thing, let's determine the angle of orientation for that spring. And so we can see here that, to get into the orientation for element B, lower number node is 1. So let's rotate counterclockwise up into the position for element B. So that's going to be 45 degrees. Okay. Okay. Then let's compute the cosine and sine of both of those terms. And so that's going to be cosine of 45 degrees. That is root 2 over 2. Sine of 45 degrees is also root 2 over 2. Okay. Okay. So this one's not going to be as nice because we don't have any zeros. And so, the only thing to do is just to kind of just compute the whole thing. Okay. Okay. So the element stiffness matrix for this spring. Okay. Right. And since we have a spring in front, instead of having AE or L, we're just going to have the spring constant K. Okay. All right. Same thing we did with the first one. So let's compute the first row and then just rotate that over. Second row, rotate that down. Third row, rotate down, and then the last entry. Okay. Okay. So first entry in the top left, we have cosine squared, right? So cosine squared, that's going to be root 2 over 2 times root 2 over 2. Okay. All right, so root 2 over 2 times root 2 over 2. The root 2's on top are going to cancel out, so that just gives you 2. And on the bottom, we have 2 times 2, which is 4. We have 2 divided by 4. So this whole thing is just going to be 1/2. Okay. All right, next entry on that first row, we have cosine times sine. So cosine, in this case, cosine and sine are the same. So you have root 2 over 2 times root 2 over 2, which we know already is 1/2. Okay. All right, next one we have here is a minus cosine squared. So that we have minus root 2 over 2 squared. Okay. So you have to be careful here. The minus sign is outside the square, and so that doesn't just go away. And so we get for this entry here, this is a minus 1/2. And then same thing on the last entry of this row. So we have a minus sine squared, and so it's a minus root 2 over 2 squared. Okay. Or excuse me, minus cosine sine. Okay. Which again, we know is minus 1/2. Okay. Okay, so let's go ahead and write these entries into the first columns. We know the top left entry is 1/2. The one right below that is 1/2. We have minus 1/2, minus 1/2. Okay. Okay. All right, next we have the next row. So the next row we have a sine square. So sine square is root 2 over 2 times root 2 over 2, right? I'm not going to write out all the multiplications just because it kind of gets repetitive, but we get a 1/2 there as well. Okay. Next we have a minus cosine sine, and so that's going to be minus root 2 over 2 times root 2 over 2, and so that is a minus 1/2. Okay. And then the last entry in that row is a minus sine squared, so that is a minus root 2 over 2 squared, so that's a minus 1/2 as well. Okay, so minus 1/2, minus 1/2. All right, so you can start to kind of see a pattern developing. And so I'm just going to write in just the rest of the terms here. Okay. Next, we have cosine squared. So cosine squared is going to be 1/2. We have positive cosine sine. That's also going to be 1/2. Okay. And then we're going to write that down. And the last entry in the bottom right here is a 1/2. Okay. I'm going to clean this up a little bit just to make things a bit more clear. So I'm going to go ahead and just replace the first row with their appropriate values. So the first row is a positive 1/2, positive 1/2, minus 1/2, minus 1/2. Okay. All right. I know it's tedious. And this isn't as bad as it could be. So, wait till you see an element with an angle of like 32 degrees, right? That is a pain to do. But for this class, I'm not going to give you anything different than like, just the nominal one. So like 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees. And so you can expect just multiples of that. Okay. No weird angles like 97 or something like that. I'm cruel, but not a psycho. All right. Any questions on this so far?
Well, actually, you forgot your anniversary, so
Well,
Not
that's
even
true.
maybe.
That's true. I'm forgetful. I'm not a psycho. I'm just forgetful.
she let you live, man.
She forgot too, so it's okay. It's my mom that's not going to let me live. My mom's upset. All right, and so remember, last thing we have to do before we move on to the next element is we have to specify which nodes are connected to this element, right? So let's go back up to the figure and look at that. So for element B here, we're connected to nodes 1 and 3, okay? And so this is going to be multiplied by the vector d1x, d1y, d3x, d3y. Oh, we can plug in for K too. So K here is, what was it, 250,000 pounds per inch. And so this K here, 250,000, that's 2.5 times 10 to the 6 pound per inch. 10 to the 5th. I'm sorry. Okay. All right. So we've only done 2 elements. We have one more element to go. So let's go ahead and plug that in. Okay. So for this one, I'm just going to go fairly quick, just because I think we're all kind of tired of these matrices now. Right. So we have element C. Okay. Element C probably is the easiest one because it's the one that's completely flat. So element C here, the angle for this one is 0 degrees. Okay, so theta here is equal to 0. Okay. So we know cosine of 0 is 1. Sine of 0 is 0. Okay. So we're in luck for this one. So we do have a 0. So that is going to cancel out a lot of terms. And so basically every term with a sign in our element stiffness matrix, we're just going to go ahead and set that equal to 0. Okay. All right. So let's go ahead and write out the values of this matrix here. Okay. Okay. So on the top left, we have cosine sine. So that is going to be a positive 1. Next, we have cosine, in the top left entry, we have cosine squared. So that's going to be 1. The next entry in that row is cosine sine, so that's 1 times 0, which gives us 0. Okay. Next entry in that first row is a minus cosine squared, so that's going to be a minus 1. And then we have minus cosine sine at the end of this row, which is a 0. Okay. And then just like we always do, let's go ahead and take this first row and write it into the first column. So we have 0, minus 1, 0. Okay. Next row, every single term in the next row involves sine, right? So we have sine squared minus cosine sine minus sine squared. And so we're just going to write zeros all the way across. Okay. And we're going to write down that into the second column. Right. Third row, we have cosine squared on the diagonal. So that's going to be a positive 1. And then cosine sine, that's going to be 0. Okay. And then the bottom right entry, we have sine squared, which is just 0. Okay. Okay. And then once again, we need to make note of which nodes that this element is connected to. So element C, we go back up to the figure. Element C is connected to nodes 1 and 4. Okay. So that is D1X, D1Y, D4X, D4Y. Okay. Oh, and then the entry in the in front. And so remember, we know that element C has the exact same properties as element A. So we know that this entry in front is going to be 5 times 10 to the 5th pound per inch. All right, any questions on this? Okay. Okay, so now that we're all done with the element stiffness matrices, the next step is going to be to assemble all of them into the single linear system. Okay, step 2, assembly. Okay. All right, so this is where things start to get messy a little bit because we need one linear system that's going to encapsulate all of our degrees of freedom. So that means 4 nodes, and for each of the 4 nodes, an X deformation and a Y deformation, okay? So that means we're going to have 8 rows and 8 columns in our linear system, okay? All right, so I need to give myself some room to do this, so let's do this. Hope this is enough space. Okay, so you have D1X, D1Y, D2X, D2Y, D3X, D3Y, D4X, D4Y. Okay, barely enough room. And then just like we usually do, let's go ahead and write these into the columns, just to kind of keep things a little bit more organized for us. So we have D1X as the first column, D1Y as the second column, D2X, D2Y, D3X, D3Y, D4X, D4Y. Yes.
Would it be beneficial if we convert the 250 to, sorry, the 5 e to the 5 to 500 e to the 3, just to keep the e to the 3 on the outside?
You could, yeah. So that's definitely one thing you can do. So, so actually the way that I did, I actually kept the 10 to the 5th on the outside, and then we just kind of add just the integers in front there. But absolutely, you should do that. Just because you don't want to be writing 100,000s in this matrix, especially when you have so many overlapping elements. Yeah, for sure. Yeah. So what I did here is, I noticed that the coefficients in front of all the element stiffness matrices are all basically some number multiplied by 10 to the 5th. And so just to make things easier, just so I'm not writing, 5 times 10 to the 5th a bajillion times on the inside, I'm gonna factor out that 10 to the 5th on the outside, and then just focus on just the integers on the inside. Okay. Okay. All right. So now we get to the fun part here. So now we get to the actual assembly. Okay. Okay. All right, so just like we did in the 1D problems, we're just going to go element by element. And so let's start with element A. So element A, we know, is connected to nodes 1 and 2. So that makes things easy for us because, nodes 1 and 2 are right next to each other on the matrix. And so we're just going to block out that 4 by 4 spot. So we're going to block out those 4 columns. We're going to block out the next 4 rows. Probably should go a little bit more down. There we go. Okay. I'm not going to write the entries in just yet. First, I want to kind of block these out just because, once you start to get into 2D problems, this starts to get a little bit challenging, and you want to make sure that you do it correctly. Okay. Okay. Next one, let's write in element C, or element B, excuse me. Okay. So element B we know is connected to nodes 1 and 3. Okay. Okay. All right. So this is where things get a bit challenging because, we are going to have to separate this element stiffness matrix out just because 1 and 3 are not next to each other. But you want to separate them according to the nodes. And so, for our 4 by 4 matrix, we're going to break it up into 4 components. And so the top left 2 by 2, the top right 2 by 2, the bottom left 2 by 2, and the bottom right 2 by 2. Okay. Okay. So for instance, for element B, nodes 1 and 3, we're going to denote this block right here. So this is the 1, 1 block. Okay. Next, we have the 1, 3 blocks, and so that's going to be this 2 by 2 here. And then this 2 by 2 down here. Okay. And then finally, we have the 3, 3 block, which is this one right here. Okay, so you can see that, I've taken our 4 by 4 element stiffness matrix and I've just kind of split it up into 4, right? By each of the different quadrants. Okay. Okay. And then finally, let's look at element C. So element C is nodes 1 and 4. Okay. So same thing with this one. And so, we're going to break up our 4 by 4 element stiffness matrix into the 4 quadrants and then assign them, according to the nodes, right? So, you have to be careful here because, when you're doing 2D problems, the X and Y deformations for a given node are kind of a package deal, and you kind of almost never separate the two, okay? Okay, so first we have the 1, 1 block. And so, the top left of our element stiffness matrix is going to be quite crowded. Right, then we have the 1, 4 blocks, and so that's going to be this one here, this one down here, okay? And then we have the 4, 4 block, which is down in the bottom right corner. Okay. All right. All right, so before we start filling entries in, let's go ahead and fill in all the empty space. And so basically any space that's not covered by an element stiffness matrix, we'll just fill it with zeros, okay? So I have 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay. Okay. All right, so now let's finally start adding entries in. Okay, so let's start with element A. Okay. Okay, so I'm just going to write in everything that's there. And remember, we're multiplying everything inside by 5. Okay. Okay, so for element A, right? Element A is given by the following matrix, right? So let's go ahead and look back up here. Okay. All right, so if it makes things easier, if you have, well, in this case, it doesn't matter. We're going to do it all in one block. But for the next one, you can block this off, right? Just like that, okay? So again, for element A, it doesn't matter because 1 and 2 are next to each other, but, we'll do that for elements B and C, okay? Okay, so for element A, first we have, first row is all zeros. And so we're going to do, 0, 0, 0, 0. Next row, we have 0. And our next entry is a 1. But remember, we're multiplying by 5 times 10 to the 5th. We have 10 to the 5th already on the outside. And so that's just going to be a 5 there. Okay. 0. And then in the rightmost entry here, we have a -1. We multiply by 5 and ends up with -5. Okay. Okay. All right, so from here, we're not going to worry about any overlaps, and so I'm going to write it a little bit bigger. So third row is going to be all zeros. And then last row, we have 0, -5, 0, 5. Okay, good. All right, so now we have element B, and this is the one that's going to be a bit challenging just because we have a lot of non-zero values here. Okay, so just like we did with element A, if it makes things easier for yourself, you definitely feel free to group these together. Okay. So, these are the four quadrants that we kind of split off into the assembly, right? So in the top left, we have 1/2, 1/2, 1/2, 1/2, okay? And remember, this is multiplied by 2.5 times 10 to the fifth, right? So 2.5 times 1/2 is 1.25, okay? So for every term here, we're going to add a positive 1.25, positive 1.25, plus 1.25, plus 1.25, okay? Okay. All right, next quadrant here, we're going to go to the right. And so that's going to be the, right to the right of that. Everything in that quadrant is a minus 1/2. Actually, same thing for the bottom left too. So this is going to be a minus 1.25, minus 1.25, minus 1.25, minus 1.25, okay? If you didn't like the decimals, then, you could do like factor out a 10 to the third in front. And so this would be 125, 125. And maybe it's a little bit more convenient. Okay. Okay. Bottom left quadrant in blue is going to be all minus 1.25s. Okay. And then the bottom right quadrant here is going to be all positive 1.25s. Okay. 1.25, 1.25, 1.25, 1.25. Okay. Okay. All right, last one is we have element C, right? So element C here, that was our flat element, okay? So this one's pretty straightforward. We only have 4 non-zero entries. Everything else is 0, okay? Once again, I'm going to take this. I'm going to go ahead and draw these quadrants in just so that we know where everyone is going, okay? So first we start in the top left. We have 1, 0, 0, 0, okay? So that's 1 times 5 times 10 to the fifth. And so we've already factored out 10 to the fifth. And so this is going to be a plus 5, plus 0, plus 0, plus 0. Okay. Top right quadrant is going to be a minus 5, 0, 0, 0. Okay. Bottom left quadrant is going to be minus 5, 0, 0, 0. And then bottom right quadrant here, that's going to be a positive 5, 0, 0, 0. Okay. All right. I know it's tedious. We're basically spending the entire lecture on this one example. But again, it's one of those things. Once you kind of start practicing these more, you start doing more of these problems. You start to kind of get the patterns much more quickly. So, yeah, it's tedious now. Especially when you're doing all the every single one by hand. But yeah, it gets slightly better, but not that much better. I was telling someone else after classes that part of the reason we're doing these problems is to make you hate doing them by hand, so that you're more motivated to do the MATLAB program. Because I think just based on your guys' introduction emails, I think a lot of people are a little bit uneasy with the MATLAB. But if the alternative to the MATLAB is to do these by hand, I think that kind of adds a little bit of motivation to learn how to program these things. Okay. All right. Any questions on this step here? Okay. All right. But of course, we're not done. Although that was by far the most painful part for sure. Okay. Because the next step here is we have to apply boundary conditions. Okay. So let me go ahead and write in our right-hand side vector, our forcing vector. So this is f1x, f1y, f2x, f2y, f3x, f3y, f4x, f4y. Okay. So step 3 is the boundary conditions, which I'm just gonna apply right on top of this, and so I'm not gonna write this matrix again. Okay. So let's go look back at our problem, and let's look at our boundary conditions. Luckily, our boundary conditions in this example are pretty straightforward because 3 of the nodes are completely fixed, and so that just basically eliminates the majority of our matrix here. And then we only have 1 force, right? So let's go back to our problem. Okay. We see that nodes 2, 3, and 4 are completely fixed, or they're pinned to the wall, right? Okay. So that means we can apply our Dirichlet boundary condition on these rows. Okay. Right, and so since each of those nodes also have 2 degrees of freedom, that means that wipes out both of those rows, okay? Okay, so let's go back up to our matrix here. So, we're going to eliminate basically everything that's below the second row, right? So first we have the D2 row. Okay, so let me actually use a different color here. Okay, okay, so the D2 row is this one right here, right? So that's D2X, D2Y. Okay. Remember, what we do with Dirichlet boundary conditions is that we basically eliminate the row, we replace that row with the 1 on the diagonal, and then we put a 0 in the forcing vector, okay? Okay, so for instance, for the second row, or for the third row, for D2X, right? We're gonna put a 1 on the diagonal. Okay, so in this case, will be the third entry. Okay. Every other entry is gonna be 0, which it already is, right? But I'll just kind of write over it just to emphasize it. And then instead of F2X, we're going to put a 0 there. Okay. And then we're going to do the same thing for the D2Y row. Okay. So once again, we're going to eliminate everything here. Okay. We're going to put a 1 on the diagonal. So the diagonal entry for the fourth row is going to be the fourth column. Okay, so we're going to put a 1 right there. And then every other entry here is going to be 0. Okay. And same thing for F2Y. F2Y here is going to be 0. Okay, so let's continue to do that. So, this is applied to nodes 3 and 4 as well. So that means the D3X row, D3Y, D4X, D4Y are all going to be wiped out except for that 1 in the diagonal. Okay, so let me go ahead and just do that really quickly. Okay, so we have 0, 0, 1, 0, 0, 0. F3X here is going to be 0. All right, and then the D3Y row, we have 0, 0, 0, 0, 0, 1, 0, 0. F3Y is 0. I realize that the rows don't exactly match up. I know it's killing me too, but just count by the number of rows. Okay. All right, next row. Still a Dirichlet boundary condition, so let's go ahead and eliminate everything just like that. And then set F4X is equal to 0. And then the last row, we need to make sure we have that 1 on the diagonal. Everything else is zeros. Okay. Okay, good. All right, so that is our Dirichlet boundary conditions applied, or our constraint type boundary conditions applied. Okay. All right. Any questions on this? Okay. Good. All right, so the last boundary condition that we need to apply here is our load, okay? So let's go back up to the problem figure, okay? And we can see that we have a vertical load of 10,000 pounds being applied on node 1, okay? So this 10,000 pounds, I mean, first of all, we know it's being applied to node 1, so that's important. But, in 2D problems, you also need to be aware of which direction the load is being applied in, okay? So in this case, the load is being applied in the y direction, specifically the minus y direction, okay? So that means the way that we're going to input it is that we're going to set F1y. F1y is going to take the entire brunt of the load. So that is going to be minus 10,000. Okay. Right, because that's the direction the load is in. And there's no load in the x direction, so that's going to be 0. All right. And so after a long ordeal, basically, almost an hour looking at this exact same problem in these giant matrices, we are done. Okay. So the last step here, of course, is to solve. I should say for me, I'm done because I've already computed this, but for you guys, this might be the painful part because you have to enter in all these numbers into MATLAB. Okay. But you do that. You solve this in MATLAB. Okay. You're going to get values for all of the nodal displacements. Okay, so that's going to be d1x, d1y, d2x, d2y, d3x, d3y, d4x, d4y. Okay. All right, so of course, we know nodes 2, 3, and 4, they're all fixed. And so you should get 0 for all of these. Okay. Right. So I guess let's put units here. So it's 0 inches. Okay. All right, and then D1X, D1Y, these are going to be the only values with, these are going to be the only entries with non-zero values. And so this is going to be D1X, surprisingly, is non-zero, even though we're applying the load in the Y direction. So D1X is 0.033 inches, okay? And then D1Y is minus 0.0167 inches. So I guess technically speaking, the only solutions that really matter are just what's in node 1, just because everything else is trivial. But that's what you get from this problem. All right. Any questions on anything from this problem? Okay, so in the last 10 minutes of class today, I'm going to show you how to do one more calculation. So, technically this problem is done, right? But oftentimes, when you run a finite element simulation, a lot of times you're not just interested in the raw solution. So I would characterize this as the raw solution. So, you basically just solve your linear system and you get the values of the primary variables, which are just deformation in this case, okay? Oftentimes you're interested in some additional properties or additional quantities that you have to do some post-processing, okay? So one of the most common post-processing calculations you're going to see in structural mechanics is you want to compute the stress, the structural stress in this structure, okay? So I'm going to show you how to do that for a truss bar. Okay. All right, so the way to do this is, basically stress, the way that we define stress in a truss bar, if you think back to, last class when we derived the element stiffness matrix for a truss bar, right? It's nothing more than just the force that the element experiences divided by the cross-sectional area. right? Because that's the definition of stress. It's just force distributed over an area. Okay. Now, this force is particular. So this force, right? Right. This force has to be along the direction of the element axis, right? And so this is force in the axial direction. Okay. Right. So that makes sense, right? The only problem now, we have the opposite problem that we had before. Where before we had the problem where our element stiffness matrix was defined in the local coordinates, and we had to go to the stationary coordinates, right? Now we have our solution, right? This solution is in the stationary coordinates. Okay. But in order to compute the stress, we have to compute the force in the local coordinates. Okay. So essentially, we have to kind of do the reverse of what we did before. Okay. But that's okay. We know exactly how to reverse this. And so the way that we're going to reverse this is that we're going to apply basically our transformation matrix. Okay. Okay, so the way this works is that we're going to focus on just the numerator here, right? So if you look at our global linear system here, or if you look at just if you look at the element stiffness matrix for, let's say, element A, okay, we basically have AE over L times a matrix times our displacement, so d1x, d1y, d2x, d2y, okay, is equal to f2x, or f1x, excuse me, f1y, f2x, f2y. Okay. Okay. And so if we were to just multiply the first row, right? And so I'm just going to kind of leave this as kind of a blank vector, right? So we just multiply the first row by this first column, then we can get an expression for, let's say, f1x, right? So we have AE over L multiplied by, the entries of the element stiffness matrix, okay? Multiplied by d1x, d1y, d2x, d2y, okay? Is equal to f1x. Where we know that the entries in here are just, sines and cosines. Right? Okay. So this is good, or a lot of this is good, because if you look at this, right? Let's look at this solution vector here for a second, right? So remember, a lot of times you're not interested in computing stresses until after you solve the finite element problem. So after you got this, okay? And so, after we've solved for d1x, d2x, and all that stuff, right? This is going to be known after solving FE problem. Okay. And we're in luck, the way that we formulated this right now, these are all in the stationary coordinates, okay? So, we want to keep this together. The only thing we have to convert is we have to convert this f1x here to the local coordinates. Okay. All right. And so, I'm gonna just for the sake of time, I want to make sure we get through this calculation, before the end of class today. I'm gonna skip the details, but the details are in the notes. Essentially, what we're gonna do is that we're gonna basically multiply both sides by our transformation matrix. And then that's going to affect the values of this vector right here. Okay. So what we get at the end is f1x hat is equal to AE over L multiplied by minus cosine, minus sine, cosine, sine, okay, multiplied by the vector of deformations for that element. Okay, so d1x, d1y, d2x, d2y. Okay. Okay. Good. So now that we have this expression for f1x, we can go ahead and plug that into our expression for stress. Okay. And so stress is nothing more than f1x hat divided by a. Okay. And wouldn't you know it, we have an a that's right there. So that's just going to cancel out. And so we have E over L times minus cosine, minus sine, cosine, sine, multiplied by d1x, d1y, d2x, d2y. Okay. Okay, so this is stress in 2D truss element. Okay. All right, so the only careful thing to know is that, when you're using this equation, this vector here has to be the nodal displacements of the nodes that are connected to that element. Okay. So I use 1 and 2 here just as placeholders, just because, I have to do 2 nodes. But, if your element is connected to, say, nodes 1 and 4, then that's going to affect your calculation here. Okay. All right, so let's just plug these in very quickly just to solve for them. So we have 2 truss elements in the previous problem. We have element A. Right, so element A, the stress in A is equal to E divided by L times minus cosine, minus sine, cosine, sine. Okay. If you recall, the angle for element A is 90 degrees. Okay. So that means cosine is going to be 0, sine is going to be 1, cosine is going to be 0, sine here is going to be 1. Okay. Element A is connected to nodes 1 and 2, so we have d1x, d1y, d2x, d2y. Okay. We plug in their values from what we obtained from the finite element solution. So d1x is 0.0033, d1y is minus 0.0167, and d2x, d2y are just 0. Okay. So we plug all those values in. We just do the simple, just vector multiplication, which is just the dot product. We get 4,175 PS. Okay. All right, so I know we're just about out of time, but let me give you the expression for element C. So for element C, our angle here is 0. Okay, so sigma C is E over L minus cosine, minus sine, cosine, sine, multiplied by d1x, d1y, d4x, d4y. Okay. So remember, element C is connected to nodes 1 and 4, right? So we do that calculation, we get minus 825 PSI. Okay. All right. I know there's kind of a flurry at the end there, but any questions on any of this? Okay, all right, so that's all we got time for today. And so when we come back on Thursday, I have another example for you guys to do for the 2D trusses. Hopefully that one won't take as long because we've already kind of practiced this. And then from there we'll move on to beams. All right, so thank you guys for coming today. Hope you guys have a good rest of your day, and I will see you all on Thursday.
Hey, Professor.
Sorry, is there someone speaking? Let me turn up the volume. I think it's down.
Hey, do we have enough information to finish up homework one now?
Sorry, can you say again?
Do we have enough learning, I guess, to finish up homework one?
So hang on. The speaker is not coming out of the computer. Sorry, could you type up your question just to make sure I get everything? Yes. Yeah. So you have everything you need for homework one. So Thursday we're going to do one more example with the 2D truss, but that example is more or less kind of the same as this one here. So yeah, you have all the information you need for homework. Yep. All right. Thanks, everyone. Have a good night. Hello. Good.